In the previous lectures, you have already studied the two radioactive decay. One was the alpha decay, and the second was the beta decay, and it was the neutron emission. So beta, we have the two type of the emission. One is the neutron emission, and the other one is the positron emission. So today I'm going to teach you the third one, radioactive decay, that is called the positron emission, and we call it the beta positive. And this is actually opposite to the what you have studied, the neutron emission. So because in this emission, it is due to the change of the proton to the neutron. As in case of the neutron, I have actually talked to you. It was the conversion of the neutron to the proton in case of the neutron emission. But this is also very easy to remember. If the positron mean the proton is converted into the neutron. So that is with the sound you can easily remember. Whenever it is the proton, that mean whenever it is the positron emission, in this case proton is converted into the neutron, and with the emission of the positron, beta positive, and there are some other particles having the zero charge and the mass, but they carry the energy. These are called the neutrino. So this is also very easy to remember. In case of the positron emission, there should be the emission of the neutrino, and the with the similar sound you can also remember the neutrino. Like in positron, proton is converted into neutron, and neutron is starting with the n, and neutrino is also starting with the n. So with the conversion from proton to neutron and also emitting the neutrino. So in this way you can easily remember whatever are the neutron or the positron emission. But here we are just talking about the positron emission. Again, if you look at the proton and the neutron, there is the proton is contributing one atomic number and one mass number, while neutron is only contributing to the one mass number. So with the conversion of one proton to the neutron, there is no change in the mass number, but there is only decrease in the atomic number. So this is opposite to the neutron emission. So in positron emission, there is decrease in one atomic number with the emission of the positron and the neutrino. So the second one is how you can calculate by using the simple equation, and this is equation is written over here. And again, you can represent any of the parent with the x having mass number A and atomic number Z converted into a daughter, that is here it is Y, and with the mass number A and atomic number should be the less than 1 as compared to the parent. So it should be Z minus 1. Whatever it is the Z, it should be 1 less than as compared to the parent. Again, positron emission plus neutrino. And this is the energy associated with the positron emission. And this you have to calculate actually what would be the energy released in case of the positron emission. And this is the equation. In a similar way, what we have used for the alpha or the neutron emission, in a similar way you can calculate the energy release in case of the positron emission, but there are certain limitation over here. Again, this is the same as we have used before in all of the calculation of the q value. This is the parent minus daughter, and then you just multiply by the c square, or when you take the difference in masses, you just multiply 931.5 the factor to convert this mass into the energy. But here it is shown over here, this is the minus 2 me. That means you have to subtract minus 2 the mass of 2 electron. So this is the actually the big reason over here. I will talk about this one, why it is the you have to subtract the mass of two electron out of this equation. And again you can see over here, this is the parent, and by looking at this equation, this is the parent, and these all, if you consider, uh, this is the daughter, and with the positron emission, that is the particle over here. And let's suppose this is the reactant minus the product, so this is the reactant minus the product. But here, in contrary to the electron emission, here the mass of two electrons are given over here, but it is supposed to be one electron because positron is having the opposite charge but have the same mass. So, like in case of the neutron emission, I'm just going to show you the what we have used before, just as a comparison. Look at this. This was the neutron emission, mass of the parent minus daughter plus mass of the one electron, because whenever the neutron is emitted, it is having the negative charge, having the similar mass as the electron is having. That's why the mass of electron you have to subtract over here. But in case of the positron emission, it is, it should be like the negatron, because it is only the difference is the positive charge, but the mass of positron is the same as the mass of the electron. So again, the question over here is why it is written over here the mass of the two electrons. So that I am going to show you in the next slide what is happening with this one. But very briefly over here, let's suppose this is the parent, and when it is converted into the daughter after the emission of the positron and the neutrino, and what is here, this is the positron, but in the extra nuclear part there are the electrons. So when this positron is coming out of the nucleus, having the opposite charge as compared to the electron, but having the same mass as the electron is having, when it interacts with the outer shell electron, it is going to annihilate. That means positron may react with the electron, and when this process is called the annihilate, they are going to be diminished. That means now they are again the mass is converted into the energy, and here energy is called the gamma rays. So I will explain more about in the next slide, but here just as an example I have given you the proof why there is the mass of two electrons are given over here. You have to subtract, and the reason is one is the mass of the positron, another one is the when this electron is going to be annihilate with the electron. So that means this is the two electrons actually is going to be released or going to be decreased while emission of the positron. So that's why it is the mass of the two electron is given over here. Very briefly I have explained over here. Now look at the equation, and this is very important equation because when you learn all these radioactive decays, and then you have to decide actually which one would be the parent or the daughter after emission of the positron or the other radioactive decay. And again, if this is the parent and its mass number is the 30, atomic number is 15, when it after the emission of the positron, there is no change in the mass number, but there is only decrease in the one atomic numbers. So whenever there is a decrease in one atomic number, that means there is the possibility for the emission of the positron. So this is the positron emission or the beta positive or the beta decay. Now look at actually the reason behind this one, what is happening and what is the process is called the annihilation process. I have talked in the previous slide. So this is the positron, and when it is going to be to interact with the negatron, because both are having the same mass but only the difference is having the opposite charge. So when they are going to interact with them, they are going to be finished with the release of the energy that is called the, here it is called the gamma ray energy. So this process is called the annihilation process, or this phenomena is it is called the annihilation process. And this is having the positron emission. Again, this is the fluorine emitting the positron. And look at the range, it is having very small range, zero point 0.1 mm. This is going to be disappear after this or some mm. So this is the positron emission range, because being a positive charge, there are the electron, and when they interact the electron with the shells, first shell is the K shell, they are going to interact with them and they will disappear with the release of the gamma rays. And this disappearance of both of them is called the term is called the annihilation, a process with the release of the two gamma rays. So here one important point here is what would be the energy of this gamma ray. This you can also calculate with the positron emission. And these two gamma ray is having a 511 kilo electron volt, 511 kilo electron volt, or you can call it 0.51 mega electron volt. If you divide this with the 1000, it will be converted into the mega electron volt, and they will disappear in the opposite direction. This is the electron. Positron is coming out from this nuclide, and when it hit to the electrons, they are going to be disappear with the emission of the two gamma rays having the opposite direction. If they are going to be disappear, or with the emission of the gamma rays in the opposite direction, that means they have the angle is about 180-degree angle. So they are perfectly opposite, directly opposite to each other. But and there is the possibility of the uh, around 0.25-degree error, and the gamma ray is not correctly having the 180-degree, it is having this one plus minus error, and this is called the equilinearity. And when they are emitted, of course we have the detector outside to detect all these two gamma rays having the energy of 0.51 mega electron volt. Now I am going to calculate this one energy. And again, there is a very simple way to calculate this one energy. And now I am also going to show you some of the very important application of this positron emission, because this is very, very important, and we use it in the nuclear medicines to diagnose the cancer, particularly the cancer in a body. And there are larger variety, and there are many types of the cancer stains, and you can detect by using this positron emission. And this is called the positron emission tomography. So what is happening again? Let's suppose this is the carbon, uh, and when it decay to the with the emission of the positron emission, it will convert it into the daughter with the emission of the positron. And of course there is the extranuclear electrons present in the k element shell. So when it interacts with the electron, they are going to be annihilated. That means they are going to be finished or disappeared because of having the opposite charges. And when they disappears, they emit the two gamma rays with the opposite direction, each of having a 511 kilo electron volt or 0.51 mega electron volt energy. And this photon, that we know there is the, because these positron and electron are having the mass, when they disappear, the mass is converted into energy. And this photon further you can use to diagnose the cancer cell, and this is called the PET detector, that means positron emission detector. With this you can build up some of the images over there to find out where the tumor is there. It will easily glow there. So but here important over here is I am talking about how to calculate the energy. And this is the positron going to interact with the neutron with the emission of the two gamma rays, each of having the 0.51 mega electron volt energy, and the total energy would be 0.51 plus 0.51, that will equal to 1.022 mega electron volt. And this is very simple to calculate in the similar way we have calculated before. This is the mass of the electron in kilogram, and this is the mass of electron in the gram. Okay, and then you can multiply with the Avogadro number. Remember, at the start we did the same calculation where we actually find out the conversion ratio of 931.5 to convert the mass into the energy. And when further you can multiply 931.5, it will convert into the this one mega electron volt energy, or 511 kilo electron volt energy. So this is the conversion of the one electron. So of course there are both are the electron, one of having the opposite charge, positive charge or the negative charge, and there each electron is emitting 511 kilo electron volt energy, and the sum of these two mega volts energy will be equal to 1.022 mega electron volt, that means emission of the two gamma rays. Now, the last, I'm going to show you how it is going to work out. Just this is an additional slide over here. Give you the importance of this positron emission. Simply, we call it the PET, and this is the positron emission tomography. And this is the equipment, and this is available in the Shaukat Khanam or the in Mole Hospital. So due to the lockdown, it is not possible to go there. Otherwise, in the previous session, we visited there, and they have a equipment there to diagnose the cancer cells. So what actually it is going to work out? This is it uses some radioactive drugs, and to the to show up some of the areas in the body where the cells are more active. So it is used for the diagnosis of some of the condition like cancers, and it also have where the cancer has spread. Let's suppose this is the tumor. Look at the as a comparison. I have shown you the three images. This is the CT scan. You can also find out the tumor, and this is the magnetic resonance imaging MRI, and this is also can be used to diagnose the cancer cell. Okay, but this is the more powerful tool. This is the positron emission tomography. So look at, actually there are no visible tumors are there, because you cannot easily find out the tumor, and that is the issue with the cancer cells. So when they are spread, then it is too late to treat the cancer cells. So this positron emission tomography, so look at the tumor, because of having a radioactive drug, when they interact with the cancer cell, they are going to glow. That means you can easily find out the tumor in the body, and to diagnose the cancer cell as well. So how actually we do the performance of the experiment? Let's suppose this is the mouse, and it is the radioactive material. You can inject the radioactive material inside the body, and then there is the nucleus with the emission of the positron. When it interact with the electron with the emission of the two gamma rays, 511 kilo electron volt, or 0.51 uh, mega electron volt energy. And when you place the body inside the detector, this detector is going to detect, and then it build up the images over there where there are the cancer cells. So these are the images I have shown over here. So this is all about the today lecture, the positron emission. And at the end, I'm going to give you one of the exercise. How can you write the your own positron emission? If maybe again I may skip the daughter or the parent, or maybe I will skip the radioactive decay over here. You have to decide the missing or fill in the blanks by looking at the other two options. So here, this is the general equation what we have learned right now. The parent is converted into daughter with the emission of the positron. Again, you can represent by the E positive or the beta positive. These are the similar symbols are being used in the literature. So this is converted into the with the decrease in one atomic number, and these are the equations are given over here. This is the boron. Again, Y is written over here. If you do not remember the name of the element, so keep writing Y. So don't write uh, uh, incorrect symbol of the element. So even you write the correct atomic number or the mass number and the symbol is incorrect, then your marks will be zero. So if you write just Y and write the correct atomic number and mass number, it is okay for me. There will be no reduction of the marks. So now the question is, what would be the this daughter after the emission of the positron? The correct answer, this is the right. It should be atomic number 4 and the mass number would be the same, and the element is beryllium. Again, if you do not remember, so don't be worried about what is the name of the element. Just put over Y over here, 4 and 8, that is sufficient. And because whenever it is the atomic number 4, you can search out from any of the periodic table or the online sources. It should be a beryllium in case of the atomic number 4. So again, it is written over here. It is very simple to understand. Now I'm going to end this lecture.